So I'll make sure he's up on the screen when I'm not doing anything, so you can see him. Oh wait, Brandon, do I have your permission now to post this on the internet with your face on it?
Yes, of course, Miss Hefty.
Okay, I just wanted to make sure.
Hello, internet.
Hello, internet. This one.
Hello to all the people who are absent today. Do what I did and come in. It's a lot easier.
Perfect. Wow. Advice. So then after that, we'll be reviewing. So test next class. We'll get round 2 in before spring break. If you're going to be absent at any point next week, I would just try to make sure at the very least, please take my advice, get round 1 done before break. So let me go ahead. I'm going to hand out the notes. I don't think these are going to take the full class. So if they don't, I have one question about interval of convergence I'd like to go revisit. And I'll give you the rest of class as time for your problem sets. How are our problem sets coming? I was, to be quite honest, severely disappointed by my problem sets from my AV class. So don't be like them. Only 3 of them were prepared to turn it on time. I have higher expectations for you all. Is it a dog? A dog! Oh my god! This was a part of last year, I meant. True. Oh my god. There were some people who always like that.
I don't miss any part of life.
Oh, yeah.
I brushed your hair a couple days ago.
Right.
And that's
Oh, if I could find it.
I can always go.
That's
right there. It's your hair. No, it's your hair. It's your shed. Yeah. A picture of her. The bunny. Oh, it's a bunny. I thought that was the bunny.
All right. So, you guys ready to start some much easier calculus?
Yeah.
Yeah, actually. All right. So, a lot of teachers actually teach this earlier in the year. I like to do it at the end because it gives us a good chance to revisit some of the derivatives and integrals. I don't know if you guys got the vibe from sequences and series, or mostly series, that we kind of stray away from what we consider like real calculus for a bit. So let's revisit. We first have to realize what parametric equations even are. Essentially, what we're going to do, instead of getting like y equals something with x's in it, we're going to get 2 separate equations, one that tells us about x direction and one that tells us about y direction. Some of you that have taken some physics classes might have seen this already when you're talking about like horizontal direction and vertical direction. We're going to kind of just separate the 2. So you're going to get 2 equations. Usually the parameter, meaning the variable for both of those equations, is going to be t. Think of t for time, because most of this stuff we're going to use in the context of position, velocity, acceleration. So let's just start with like, how do we draw a graph? How do these things interact? So we're going to plug in some points. We're going to draw a picture. I'm going to do one, and then you're going to do one. All right. So I'm going to make an XY table. You may say, Hefty, there are 3 columns in that. And that's because I'm going to do a TXY table. Because I'm going to plug in values of t, and then I am going to get x's and y's. What's probably, this is a think about it question. What's probably the lowest value of t I should use?
1.
Why 1? Perfect. All right, so we're going to plug in 1 to these guys. So square root of 0, last time I checked, is 0. And then 1 plus 2 is 3. So what did I just find? I found a point, and that point is 0, 3. So I would plot it right here. Wow. All right. What point would you plug in next?
2.
Wow. All right. The square root of 2 minus 1 is the square root of 1, which is? Cool. 2 plus 2 is?
4.
I have plotted the point 1, 4. Don't worry, by the end we'll be integrating. That is the funny part about unit 10 is we go from like plotting points to like integrating between two curves. Yeah. For fun. All right. Now, I don't think I want to plug in 3. Does anyone see why? The square root of 2, that's not a fun graphing number. What would I plug in next? 5. That sounds great. 5, because the square root of 5 minus 1 is the square root of 4, which is 2. 5 plus 2, last time I checked, 7. Let's plot the point 2, comma 7. I think that's here. 1, 2, 3, 4, 5, 6, 7. Cool. No, you're not. All right, I know it's kind of at the top of the graph, but what point would you plug in next? Let's say you wanted to plug in another one. 10. That would give me square root of 9, which is 3. 10 plus 2 is 12. So essentially, I'm going to keep going up this way. Now, you might notice me adding something to this graph. Did anyone notice that I added some arrows? One cool thing that we get when we do a graph with parametric is we actually get a specific direction the graph was made in, because you're kind of adding in this third thing that gives an order to the points. So thinking of t like time, there was a certain like chronological order almost to the points. So we denote that on the graph by drawing those little arrows. What does this graph kind of look like? Yeah, is anyone getting parabola vibes from it? All right, so let's see why that's the case. We're going to do something called eliminate the parameter. What that means is we're going to try to solve one of these equations and like plug it in so that we have y equals something with x's in it. I'm going to choose to solve the second equation for y just because it looks easier. And by solve it for y, I mean solve to get in terms of y. So I have t equals stuff. So I'm going to do y minus 2 equals t. So eliminate the parameter. I want to get rid of the t, essentially. I'm going to take that guy and plug him into the x equals equation. You could also do this by solving for t in the x equation and plugging it in the y. It doesn't really matter. So I'm going to put y minus 2 where the t was, minus 1. Let's see. Usually I have my equations in y equals, so I'm just going to solve for y. X squared is y minus 3. So y is x squared plus 3. Would that make a parabola? Would that make this parabola? Yeah, how do you know? Yeah, that 3, we will want the x-intercept. Now, why do you think we only have half of this parabola? Why is the other half gone? I don't know. Why did James say that the first number we should plug in is 1? I can't have negatives. So I would argue that there's a kind of specific domain restriction on this one. So we'd be looking only at x's greater than or equal to 0 because of this square root. So there can be like domain restrictions based off of what's going on. All right, what I would like you guys to do is graph the next one. If you are feeling great about it and you go fast, you can try to also eliminate the parameter. All right. I would recommend plugging in your integer values for this one. So I would recommend personally plugging in for t -2, -1, 0, 1, 2, 3. Those are the ones I plugged in. You could plug in less, plug in more, but that gave me about the right amount of detail. Let's take just a second to graph. And by a second, I mean 4 minutes. Have fun. Oh, it's the happiest I've heard you guys in a while. But I guess that's a good thing. Who would want a teacher who doesn't like what they're teaching?
Do we eliminate?
If you want to, you can. I will in a second. So if you're done graphing, you can try to eliminate the parameter. If you're not sure how to connect the points, eliminating the parameter might help you see what kind of graph it should be. So you would be finding t and then plugging it into the other equation. So whichever one looks easier to solve for t, you could do, and then you're going to plug that in where t is in the other equation. Usually we'll solve for y. This one I wouldn't solve for y because this isn't really a function. Yeah, I would based on the shape. It doesn't matter. Honestly, none of what we're doing right now would ever be on the AP exam, and I'll talk about why. Did we do any calculus? Yeah. Why would I spend an entire class teaching you something? No, I don't do that. All right, did you get a similar graph? Yeah. Excellent. All right. Did anyone try to eliminate the parameter here? You started? Was anyone who started going to solve for the bottom equation for t? I thought that looked easier. So I was going to do 2y equals t. So x equals 2t squared 2y. I just wanted to say 2t really bad. It's just fun. Oh. All right. 4y squared minus 4. So that makes sense. Sideways parabola, x equals something with y squareds in it. Feels right. Now, if I look at what we're doing right now, this is kind of giving us a feel for what parametric is, but kind of like I was saying up here, this is not the kind of stuff that's going to be on our AP test. What is going to be on our AP test and therefore on my test is taking derivatives and integrals. Now, for the most part, parametric derivatives work almost exactly how you would want them to. I say almost because the second derivative is a little bit weird. But other than that, they really do work the way you want them to. So we're going to practice with our derivatives. We'll do 3 different questions. We'll take a break, and then we'll come back and do the one integral thing we do, which is the return of arc length, which you probably forgot about. So,
Miss Hefty,
yeah, Brandon.
what are the bounds for on the bottom of this question?
So yeah, actually, it's a good question. So you're talking this right here.
Yeah.
So that part is giving us a very specific place to look at this graph. So that's why I ended this graph with dots. So this graph doesn't have any sort of domain restrictions on t like the last one did. This one up here, I ended it with an arrow because that would kind of go off in the direction when we didn't have any kind of exclusive area we were looking at. So they just might give us a specific place to look at on the graph.
Okay.
That's actually, if you graphed in the calculator, you'd have the same thing. You can graph for a certain amount of t's.
I just thought that the domain was in like X, so I was wondering why it went to -4 on the left and 5 on the right when it says -2 and 3. You know what I mean?
Yeah, so the t is going to be kind of like the time interval that we're graphing between, and then so I'm probably using the word domain wrong. The t is giving us like an interval of time that we're working on, essentially.
Okay.
All right.
So it's like the domain like thing isn't actually on the graph. You can't see it.
Right. So it's kind of more like just the values of t that we're allowed to plug in to find.
Oh, okay. Right. So the values we plugged in were no more than. Okay, got it.
Yep. All right. So let's talk derivatives. dy dx works exactly the way I want it to. I take the derivative of the y thing and I divide it by the derivative of the x thing. That was a very strong reaction to that derivative, James, but funny bone? Or think, oh, sorry. It looks like it. So I think this works exactly the way I want it to. I want dy dx. I'm going to take dy dt and divide it by dx dt. Now, what I'm about to write down isn't exactly legal, but does give me a very good algebraic looking thing. So I know these aren't fractions, but I'm going to treat them that way because they look like it for a second. I'm going to take dy dt, and instead of dividing it by dx dt, I'm going to multiply by the reciprocal. There were some very strong air quotes there if you couldn't see. So by dt dx, what does it look like is happening? Yeah, it looks like the dt's would cancel effectively, and I would get dy dx. While that's not exactly what's happening, because those aren't really fractions, it does give us a kind of algebraic representation of why this works the way it does. Really, we're just doing the rate of change of y over the rate of change of x to get the rate of change of y with respect to x. So, works. Now this one, you're not going to like. I'm going to show you two different ways to think about it. One that's like this algebraic workaround, and then I'm going to show you kind of within the context of a question how I could work it out, and then kind of how you would actually do it. Our second derivative is a little bit weird. For parametric, we can't actually just take the derivative of the first derivative and say we're done, because taking our second derivative with respect just gets a little bit weird, to be quite honest. So this is the formula we're going to end up doing. We're going to take the derivative of the first derivative, but then we have to again divide it by dx dt. I'm going to show you kind of with this reasoning, like I did for the first derivative, why that's true. You might not like that, so I'll show you a different way. If you don't like that, I can try to explain it again, or you can just accept that it's true, and we can move forward with our lives. So let's say I take this numerator again, this guy right here, write him out, and multiply again by the reciprocal of the denominator. I know they're not fractions. I'm going to treat them like them. Oh, I messed up. Fixed it. All right. Again, here, this looks like I'm taking the dt's and canceling them. And so I get the derivative with respect to x using the kind of d from the first part, dx from the last part of my derivative, and getting my second derivative. So it algebraically, even though it's not really legal, it kind of algebraically looks legal. I'll show you within the context of the question again, a different way to kind of justify that, but really you're probably going to end up kind of memorizing this process. So let's do 3 questions. All right. this first question, look at how easy this is going to be. We have two equations, one that describes the x direction, x equals t squared plus 9. Don't you just want to take the derivative of that right now? How easy would that be? All right. And then we got a y, and then we're finding dy dx and the second derivative. So let's do dy dx first because that's going to be easier. So we're going to do it super explicitly at first. We got dy dt and dx dt that we have to find. Now, you may be like, why are you writing dy dt first? Because sometimes I write dx dt on the top and then I divide the wrong way because I'm a doofus. So I do y first, so I'll make sure it's on top. So what's the derivative of 4t to the 5th minus 6t cubed plus 3? Wow. All right, even easier. What's the derivative of t squared plus 9? 2t. See, I got to say it here. All right. Now to find dy dx, I'm going to divide. I'm going to do dy dt over dx dt. And I don't know about you, but that's like screaming at me to simplify it. All right, what would our first term be after simplifying? 10. Yep, minus 9t. Perfect. So that's dy dx. We're done there. I want to show you a different way to find the second derivative than just kind of using a formula. So this is another justification for why the second derivative works the way it does. I'll make some comments at the end as to what my students normally do to find the second derivative. So I'm going to roll down here because I'm going to need a little bit of room. All right, so we're taking the derivative with respect to x of our first derivative. Does anyone see a problem with what's going on right here? That's a very big question, but I want to see if you see it. All right, that may be a problem. We didn't give ourselves enough space. Yeah, so we're taking the derivative with respect to x, but the letter in my equation is t. Been a hot second since we did something like that, but we did it back in related rates. Does anyone remember what we did if those letters didn't match? Y'all are thinking too hard. All right, let's just take the derivative first and then we'll think about it. So what's the regular derivative of 10t cubed? 30t squared, right? Now, let's say these were y's instead of t's. Does anyone remember, like, implicit what we would put after it? We'd put dy dx, right? Here it's a t, not an x, so what do I put? dt dx. All right. Sorry, I should have warned you. All right, what do you think 9t is going to turn into after our derivative? dt dx. Now, I could factor this dt dx out. And I don't know what dt dx is, but I do know what reciprocal is. So would you agree this is the same as 30t squared minus 9 divided by dx dt? So instead of multiplying by the reciprocal, I'm just dividing. So that is why we need to divide by that dx dt. So I really just want to do 30t squared minus 9 over 2t was our original dx dt. Now, do my students usually do that entire process every time? No, they're usually quite lazy. So usually what they do instead is they take this and they're like, okay, I'm going to do the derivative of the first derivative, so 30t squared minus 9 with respect to t, and then they know they have to divide it by 2t. I just wanted to show you a couple of reasons as to why we're dividing by dx dt, because that is usually when I do like a mastery test or highlight this test, whatever I'm doing, that's usually the biggest mistake on the parametric part. All right. So my answer's that guy in green and this guy in pink. Easy enough, right?
What's the reason?
So remember in like implicit derivatives, so let's say you were taking the derivative with respect to x of like y squared. If these letters didn't match, we were like, okay, let's take the derivative normally and then do dy dx. Yeah, so it's like a chain rule for that function. Same idea. If the letters don't match, we have to do that d whatever. Same thing with related rates. All right, so now that we know how to take a derivative, what's our most classic application? Let's do a tangent line. It's been a hot second. How do we write a tangent line? Let's start you off. Y minus. What is that? Good Lord.
Y minus y1.
Oh, thanks, Brandon. Y minus y1 equals m x minus x1, right? All right. What's the calculus part of all of this? Where do I put the calculus part? M is my slope, which is my dy dx. All right. So I need a slope. I need a point. Now, this is where parametric gets a little obnoxious. I obviously don't have a slope yet. They didn't tell me that. Do I have any part of the point right now? Do I have an x value or a y value? Yeah? I have x equals a number and y equals a number? Yeah, so I'm going to have to plug in a t. So I have to use t to find both x and y here. So Jess is just braver than the rest, or me, I guess. All right. You guys like trig?
Not really.
If you don't like trig, I would recommend just maybe peeking at a unit circle over spring break. Polar's not fun if you don't like trig. All right. So do you guys like Jess's idea of plugging in 2 pi over 3 to find x and y? All right, so 5 sine of 2 pi over 3 and 3 cosine of 2 pi over 3. Do we know what sine and cosine of 2 pi over 3 are? Or do we need to draw a picture? All right. Yeah, just close my eyes. All right, where's 2 pi over 3? What quadrant? 1? 2? 1, 2, 3, 4. All right. So if you're imagining a triangle, your longs and shorts. Does anyone do that? Longs and shorts? Nice. All right. Do we know what the two choices for sine and cosine of 2 pi over 3 are? Square root of 3 over 2 and 1/2.
Negative 1/2.
Fair.
Is it negative or is it positive?
You're right. The 1/2 is actually going to be negative. So let's talk about 5 sine of 2 pi over 3. We're talking this right here. This is the y value. So we've got 5 times the longer of the two choices, and it should be positive because we're above the x-axis. So this would be 5 root 3 over 2. Hello. All right. This one's going to have a 3. This will be the shorter of the two choices, and Brandon is right that it will be negative. So we'll have 3 times negative 1/2. So your trig doesn't have to be fast. Never ask you for fast trig, minus maybe the first quadrant. All right, so we got points. We got a point. We don't have a slope. How do I find slope? Derivative. Whoa, long callback. All right. All right. So how do we find dy dx for parametric? The derivative of y over the derivative of x. Magic. All right. So y is 3 cosine t. What will be the numerator in my derivative? Anyone? What's the derivative of 3 cosine t? Can you not remember if it's negative or positive? Is that the
Negative
problem?
sign, right?
Why'd I leave a space? 3. All right. What's our derivative of 5 sine t?
5 cosine t.
Thank you. All right.
Sorry, all my responses are going to be like 2 seconds delayed.
That's okay. You're confirming what the class said. All right. So I'm going to now plug in my t value. Oop, not like that. By saying this notation, I like this notation. It's from our main man, Gottfried Leibniz, the true creator of calculus. Not Isaac Newton. All right, so I'm going to plug in my t value. On the top, what did we say sine of 2 pi over 3 was? Root 3 over 2. All right, and we said cosine was negative 1/2. Now, I could theoretically chuck that whole thing into my slope and not simplify it at all, but let's just try to clean it up a little bit because it looks gross. What would you guys kind of cross out in this case? And would you cancel anything? Nothing? Yeah, I would cancel the halves. And then I might make both these positive, personally. So I'm going to roll with 3 root 3 over 5 as my slope. So I didn't give myself anywhere to write my answer. Right? Oh, let's just put it, should we just put it up here? Yeah. All right, let's just go. Yeah, let's just go in the middle. I'll label it answer so I know. All right, I'll start you off. Y minus what? Y1, which was what? Negative 3 halves. So I'm going to do y plus 3 halves equals what number? Slope. All right. Then what? All right. Sick. I wonder if Desmos will use the graph parametric. I bet it doesn't. Let's try. Yeah, I'm wondering. Let me see if it'll work. Your calculator does. Oh, probably shouldn't type that in. Just do I have parametric mode? I know it graphs in polar. I don't know if it'll graph in parametric. Ooh. I'm gonna go with no on that one. All right, so let's see. All right, I'm gonna pull up my calculator in a second, but let's look at these last ones before we take our break, and I'll probably show you some graphs when we get back from break. So, one more? One more? No? All right, let's do this last one, and I'll show you some graphs when we get back from our break. Here's another way we could do this relatively easily with our derivative questions, another relatively easy application, if you will. So we're going to find all of the points of horizontal and vertical tangency given the parametric equations here. So what that means, where are their horizontal tangent lines? Where are their vertical tangent lines? Let's remind ourselves one more time of how we find dy dx to help ourselves out. What 2 things do we divide for dy dx? Okay. So let's say we're doing horizontal first. What kind of slope do horizontal lines have? 0, right? So we want dy dx to be equal to 0. If we want dy dx to be equal to 0, which one of the things in the fraction should be 0? dy dt or dx dt? So if I want this whole fraction to be 0, the top one should be 0, right? So we're going to try to set dy dt equal to 0. All right. What is dy dt? Isn't that something you would love to set equal to 0? T equals what? 4. Now, it said find the point of horizontal or vertical tangency. Did I find a point? No, I did not. How could I find a point? Plug in the x and the y. So I'm going to plug in, what is it, 4? That's annoying. 3 times 16 is 48 minus 6 times 4 is 24. That's 16 minus 32 plus 9. Ew. I'm going to go 24, comma, negative 16 plus 9. It's negative 7. Weird point. Little off to the right of my graph. Little down. All right. Why don't you guys try vertical? When we want a vertical line, what should be true about the slope? No. No. Undefined.
Oh, right. Yes.
All right. How do I make that fraction undefined? Yeah, put a 0 at the bottom. So you're going to set dx dt equal to 0. Can you follow through the rest of that process? I'm going to try to get you some graphs, and then we'll roll into our break. Parametric mode. All right, which one should I do first? Let's just do this one. 3t squared minus 6t squared minus 8t plus 9. Why is the T max set at too high? Why would I ever do that? Actually, that'll work relatively well. You guys done already? Is that why we're giggling? You guys hit T equals. Yeah. All right. Plugging in to get my point. Let's see. I've got, oh, one's easier. Negative 3, comma 2. Is that wrong? Okay. Cool. All right, so while you guys were working on that, you might have seen I kind of went to the graph. So what I did, this isn't super necessary, especially for the AP test. You don't really have to, so you can play around with it if you want. On the calculator, notice I changed the mode from function to parametric. You might have actually changed it back because math analysis has been working in parametric mode because they've been looking at some of these equations. If we change to parametric, look what happens in y equals. There's a space for our x equation and our y equation. Now, one weird thing about the TI calculators is you kind of have to tell it what values of t to plug in, kind of like that second graph example that you guys did on your own. So for here, I don't know why it was set like this. It's set between 0 and looks like 2 pi-ish. The T step is kind of how often it will check for points. So like on our first one, we were checking for points every T equals 1. We were counting by ones. This is counting by something that's some small fraction of pi. and it's starting at 0. So if we look at this graph, think of the 2 points we got, -3, 2. I could probably trace that. If I press trace, I can plug in our t equals 1. Notice that we get the -3, 2 on the bottom. Does it look like at that flashing point there would be a vertical tangent line? Yeah. And then we had t equals 4. Hopefully this is in the window. Yeah, over there, we've got our 24, -7. Does it look like horizontal tangency would work there? Yeah, probably. I use trace. This is my favorite button on the calculator. You can plug in whatever t value you want. So since we got t equals 4 for the first one, I pressed 4 and enter, and it will locate that point. And you can do that on XY graphs as well, like our regular function graphs. Trace will work the same way. All right, that's about all I want to talk about for derivatives today. We're going to talk about one application of integrals when we get back, and it's actually going to be super simple. So let's take a solid break. Let's go 5. All right, 5 minutes. I'll see you back here. Please don't fall down. Is it raining again? Light rain forecasted. Oh no. I forgot to take a quiz to a kid. No.
Just throw it at my head.
Do people want to see Bailey again, Miss Hefty?
Oh,
That involves leaving the
yes, God, please.
Taking a quiz to someone? Yes. Go to Miss Francis, room 162.
162.
Do you know where that is?
I can find it.
It's down in this hallway.
Okay.
Say that is for Constantine.
Constant.
He's a very nice child. I think the question.
162.
Yeah, I'll ask people if they study halls in a different room. Oh, it's study. I know. It'll be like the first question you ask. Well, she was like that with me. It's like by the time I got to my second question, she doesn't like them. She called me chubby fingers. No, which one? What? Austin and Ellen. Oh, not you, Austin. Yeah, my fingers are like small, but she called them chubby because I was like mistyping the calculator, and that's how I got questions. So I don't think she's actually talking about the size of your fingers. Yeah.
I would internalize very quickly.
Every time in the viewer.
Sorry, I have like spider hands. They're really long.
No, did I mention it? Like, I saw it, but yeah, like, my fingers look so. It's funny how it's
How's your break going, Miss Hefty?
What?
How's the break over there?
The break has been thrilling. Yeah, how's your break going?
I'm enjoying quality time with my dog.
Oh, nice.
Yeah.
Can we full screen you?
Yeah, click on my face, I think. There you go. Hold on,
That's
let
as
me.
big.
Hold on. I can help you a little bit.
I did an assessment.
Was he happy to see you?
He was at counseling earlier.
That's
So
okay.
his friend said he might have time to, or he might not.
That's okay. Thank you. Brandon's gone.
All right, Bailey. Time to do more calculus.
All right. I'm going to ask you a question that I'm going to predict no one knows the answer to.
Okay.
It's a number.
No. Does anyone remember the formula for arc length from Unit 7? There was an integral. It had big square root in it. All right.
Is it 1 over x squared minus something?
No. But there is a 1 in it. So that's the quadratic formula. All right. I'm going to write it down, and you're going to tell me if it looks familiar at all. So it's going to have bounds. It's going to be a big
Is
square.
it 1 plus in the bounds 1 plus like the slope or something like dy and then times
What goes in the parentheses?
dy
F
dx?
prime. Okay, so this we got a long time ago for what's called arc length. Do we remember what arc length even means? All right, so the length of something curvy. So I'm going to write down the formula. It's a senior? Nice. All right, I'm going to write down the formula for arc length for parametric graphs, and you're going to tell me if you want me to algebraically prove why it is the way it is, or if you want to just roll with the formula. Both answers are acceptable. I didn't leave any room because I don't want you to write down the proof, but if you want to know where it comes from, let me know. I think it makes some sense, though. So we're going to go, I'm going to write t equals a and t equals b just to emphasize that these are going to be times here that we're plugging in, or values of t if you don't want to think it as time yet. Still a big square root. Yes, please write this part down. So this is going to be like a formula we'll use. Now, instead of having just 1 plus the derivative squared, we've kind of got 2 derivatives that we're working with. So we're going to have either direction works, but I'm going to write this one first. dx dt squared plus dy dt squared. I think it kind of looks similar, kind of has similar vibes. Would anyone like me to prove why that is the way it is using algebra? Sure. All right. Then enjoy the show. All right.
Sefki was just waiting for one person to say yes so she could explain it anyway.
No, I actually didn't really want to explain it, but that's fine. I will. No. But if someone wants to know why this is the way it is, you deserve an explanation. So, all right. So what I want from you, if you don't care, take like a 5-minute power nap. If you do care, just watch and just make sure I don't make any algebra mistakes. I won't even ask you questions. I'm just going to explain it. So I'm going to replace, so I'm going to work off of this one that we already proved. We did this with Pythagorean theorem a while ago. I'm going to replace the f prime with what we just got for the f prime for our derivative for parametric. So I'm going to go dy dt over dx dt. And that's going to still be dx. Let's see. In the next step, I'm going to kind of, I hate using this word, but distribute the squared to the top and bottom of this fraction. So if I square a fraction, I can square the top and not change my variable. And I can square the bottom. All right. I'm not loving that I have that fraction and I have that one chilling off to the side. So I'm going to make this into one fraction by calling this one dx dt squared over dx dt squared effectively. So I'll have the square root of all over dx dt squared. This will be dx dt squared. So right now that's the 1 plus the dy dt squared. Legal so far? Anyone who's paying attention? All right. Let's see. I am still not loving that fraction. So I think I'm going to square root top or not square root top and bottom. Kind of. Yeah. I'm going to do essentially this process in reverse. So I'm going to, we have the square root on both parts. I'm going to square root the top. And I'm going to square root the bottom. Now, square rooting the bottom, it's already squared. So would you agree that that can just be dx dt? Is anyone paying attention? Yeah. Oh, okay. If I square root this, am I going to get this? Okay, cool. Keeping my dx on the end. All right. I don't like dividing by a fraction. I'm going to multiply by the reciprocal. So I'm going to multiply by dt dx. That's non-x. What's the last thing you think I'm going to do? And I'll have dt at the end. Okay, so it's coming from something we knew before. I think it still makes a lot of sense, though. We have a lot happening with like derivatives being squared, square root. So though it is a completely new formula, it's coming from a pretty good place. All right, if you decided to take a power nap, now would be the time to wake up. I need about less than 5 minutes more of your time. So these questions are pretty darn explicit. They also usually come up with these words, which are glorious words, because that means I just need to set it up and then I'm going to leave it. They usually don't even make me evaluate these on the calculator because that's obnoxious to put into the calculator. So usually these are a setup but do not evaluate. So I'm just going to go straight to the integral. Let's start with looking at this one. We have the arc length of the curve. E to the 5t plus 2 is our x. 3 sine of t squared is our y. You can probably predict what derivative rule is going to come up quite a bit. We're working between 0 and 4 for t. So what are our bounds? Let's start there. 0 and 4. Wow, I'm not surprised. All right, I'm going to write a huge square root. What? Like that? You don't like that? Okay. You do you, man. All right. I'm going to do dx dt first. What is the derivative of e to the 5t plus 2?
5t plus 2.
I don't think I heard a single person forget that chain rule. So proud. So proud. If you did,
Good thing I had my mic muted.
All right. Speaking of chain rule, what is the derivative of 3 sine of t squared?
Negative 3
All right, let's
cosine
just do-
3.
All right, let's do, what's the derivative of sine? Cosine. And does this one have chain rule?
Yeah, it's
What
c
should I
squared,
multiply
right?
by? by 2t, square it. I'm just setting up. Does it matter if I simplify? Absolutely not. Yeah, you could do 6t cosine of t squared. That's perfectly cool too. Have I finished the question? Yeah, it's one of the few times when I asked that question that we actually have. We have set up an integral expression, meaning an integral without an equal sign that represents the arc length of this curve. We did not evaluate. Yes? No, so the dt is outside the square root. All right, you guys think you can do the last one? Cool. I want you guys to try the last one. Something's going to be missing. We're going to use the calculator to find out, so I'm going to plug in. Wow, James, what a brilliant observation. Spoiler alert. Oh no, I wrote the wrong one.
Oh, wait, there's no two in that one. Yes. Okay. I don't even know if that works.
Look at how cute he is. If you restrict it, it can look like a butt. I don't think right now it does.
Like four.
4 butts. All right. I'm gonna write down what I think it is. All right, what did you guys write for dx dt? Anyone want to volunteer their dx dt? Michael, what'd you get?
Negative 5 sine t. I also got that. Minus 5 times sine 5t.
Who I want?
Or plus.
Plus, thank you. Perfect. All right, does anyone want to volunteer their dy dt? I did not leave myself in the room.
I can do it, Miss Hefty.
All right, James started, but you can give me the back end, Brandon, if you want. He started 5 cosine t.
And in the back end, I have minus 5 cosine 5t.
Beautiful. All right, I'm going to extend my square root over, and then Jill asked a really good question. That dt does need to be on the back end, not inside the square root. All right, James was also right earlier, noticing that our bounds are missing. So I want to show you a graph and then ask you kind of an intuitive question. So this is what the graph of this looks like. Looks kind of like a clover or a butt, depending on what you see. Now, there are a bunch of angles in here, right? There's a bunch of sine of something, cosine of something. If you had to bet money on what you think those bounds are, what do you think they are? Think of like circles and the unit circle. How long does it take all the way to get all the way around the unit circle?
It's like 5.
It's usually like 2 pi, right? So I think that's the window I have right now, but let's just try a different one. Let's see what 0 to pi looks like. I'm just gonna play around on my calculator. Now it really looks like a butt. All right, so that's half of it. So I think that 2 pi window is enough to get all the way around. And we'll talk more about this when we hit polar, because a lot of those graphs, we will have to figure out how long it takes to get all the way around those graphs, because that's going to be dealing a lot with angles. But that's going to get me all the way around. Now, they would probably either tell you that in the question or give you a picture, something that would help you determine that. But we're going to go with 0 to 2 pi. Also, just keep in mind, again, we are setting up but not evaluating, because the odds that every single one of us can put that in the calculator and get the same number, I don't think that's happening. So There we go. That's parametric equations. So you'd probably, with sine and cosine, you'd probably want to bet it's 0 and 2 pi. You could start plugging in some points and seeing if you could figure it out. If this were a question I would give you on the test, I would give you an interval to work with. So this one, you would probably either get a calculator and you could play around with the window and the T min, T max, or I would give it to you explicitly. Cool. All right, let's do some announcements. And then I'm actually saving the notes check for next time because I'm more interested in the vector part of this than the parametric part of this. So we'll do kind of a more extensive notes check next time. Oh, other things. Remind me for the zillionth time. What's happening next class? Test next class. Let's say, oh, wait, no. I lied. I want to do one question. Frank. Happy April Fools. All right, we're going to do some announcements. And then I would like to play Sit, Stand, Hover personally. But, Sit, Stand, Hover. Have we not played?
Oh, yeah. Let's do it.
This one? All right. We'll play in a second. Yeah. All right. So we'll do this in a second, but I just wanted to show you for the test, if you're looking for some practice questions, your problem set is probably the best reflection of the types of questions. They're going to be easier than the problem set, but like the types of questions that I'll ask. I believe I got this test from a different teacher in the county a few years ago. So if you're just looking for some especially good multiple choice questions, there's also a really good example of Lagrange. This 12B right here is a really good example. I have this printed so I can give this to you if you're just looking for more practice. The key should be at the bottom here. So if you're looking for practice and being able to verify that you're kind of doing stuff right, I have that for you. That is an optional experience though. Would you like to play a game?
Yes.
All right. It's called Interval of Convergence. All right, if you want, this is all right. Let's play a game. This is the back of your 9.2 notes if you want to play along on paper, or I'll get the whiteboard stuff out if you want to play there. We're gonna play a game I like to call Sit, Stand, Hover. You can choose which ones stand, and which ones hover. So we're gonna say which one of these statements must be true, may be true, or cannot be true. What do you want must be true to be? Stand. What do you want may be true to be? Sitting, hover. That's fair. And then cannot be true, we're going to sit. All right. So I'm going to tell you about this power series. Could you tell me where this power series is centered? -3, because usually we see x minus the center. So I'm going to tell you that this series converges at -8 and diverges at 6. I'm going to give you 5 minutes to decide if it converges, diverges, if these statements must be true, may be true, or cannot be true. Ready? All right, so back of the 9.2 notes, but I also have a whiteboard that I'll pull out for you to just copy. You get 5 minutes. Everyone play. Is everyone ready? We can play a game at the end of class. Oh, I have really good ones. All right. I'm going to give you 5 minutes. Okay, so it has to and we don't know about oh, that's the best score instead of bonus point or something.
So,
I think,
Whoever gets the least amount of points.
whoever gets the point out, get the person. Like when I was like A.
Oh, I think I guess.
oh, you
It has some meaning. You're talking about how far away the things are. I was thinking about
Oh wait, you like
So, like,
so K is basically what?
Go ahead.
Oh wait,
So if we're scoring,
Yeah. Wait, it's supposed to be a ratio test and then
if negative
and then
we're closer to the center, if this was right, so I know it's anywhere between -3 and -8, but also -3 up.
Are y'all in agreement with this?
No. Yeah, I think you're right. So, we know that.
So,
No. Now he comes out and freaking little. You got Brad interval conversion, right? We know that conversions at the center. We know that conversion.
that's why you can already answer one. I think I did
That was a while ago.
yeah.
Ooh.
I get to the end.
I try to not do that.
There's so many people that do that. One teacher.
I'm not that bad, right, with grades. I know I take a while to grade some tests, but
That's not good because I know the test is good. Oh my god.
yeah, I feel like I can take a while to grade writing because like I don't know.
Yes, I am. Yes, I am. I don't understand why you can have weekends. Not grade at least one of the 18 labs.
Do you do work on the weekends?
She was so sad. I was so sad when you had this. I'm like, that's great.
All right. Anyone think they know any of these? Anyone feeling bold about any of them? All right. Let's take a second to talk about what I'm asking you, and then maybe we'll see. So I drew some extra stuff on the board. So we know for sure that which number converges. Which? Okay, fair. We do know that -3 converges. They also told me something else converges. -8. Now, let's think about this. If -8 converges, that could be the end of our interval of convergence, right? That could be the outer, like the farthest I can go away from -3. So what if I asked you about a number like negative, this isn't on here, but what if I asked you about a number like -7? All right, why does that have to converge? All right, if -8 converges, that could be the absolute smallest the interval of convergence is, but if -8's in the interval of convergence, anything closer is in the interval of convergence. Why did I draw that pink stuff underneath of -8 and -3 and kind of in the other direction? All right, there's two sides. So how far could I go over here?
2.
How far is that? Brandon said 2. He is brilliant. Why did he say 2?
-5 + 5.
Yeah, so this is -5 this way, this +5 this way. So let's play sit, stand, or hover. This one. The power series converges if x equals 1. If it must be true, stand. If it may be true, hover. If it cannot be true, sit. We understand. Good. We are standing because this must be true.
Bailey.
Brandon stand? Yes. All right. I have another question. All right. Next one. Power series converges if x equals 2. Sit, stand. Here's a demo of hover. All right. We should be holding a spot. Why are we hovering? All right. We have to test endpoints. And like Lily asked me earlier, just because one endpoint converges doesn't mean another one converges. All right. May be true. Now, some other people, you guys can sit if you want. All right. Which one do you already know? I heard this one. This is the most convincing one I heard. Which one do we know cannot be true since you're sitting? The last one. Why can the last one not be true? It has to converge there because Jill's reminding me that's the center. All right. Any other ones we're convinced of right now? Let's look at the other one. All right. We know we do what at x equals 6? Did they tell me about that? Diverge. So that's possibly the largest interval of convergence. What number could I put over here? Think of what Brandon told us. -12. I like that. All right. So we're doing +9, -9. So let's talk about x equals -10. What are your thoughts? That would be like right here. I would go with the hover as well. It's out of the may of true. Wow. That's outside the known convergence, but it's not outside the known divergence. Is there another one that may be true that you can see? -9. All right, thoughts on the last one?
Cannot.
This one, yeah, Brandon. Sorry, I wrote it already.
It's okay. You said what I said anyway.
All right. So this one, yeah, sorry, I didn't color code at all. Must be true for that one. Why must that one be true?
It's outside of the series.
Okay, so it's further away from the center than something I already know diverges. So here, let me fix the color coding. This needs to be pink. And then this needs to be yellow. Does that help? Those that don't like that. Erase the boxes. I can do. Okay, sorry. No, you're good. You want the blue box to be yellow. Got it. I can make that happen. I love OneNote. It's great. All right. Thank you for playing this round of sit, stand, hover. I apologize. It took longer than I wanted, but I think you guys noodled that quite well. So
let me give you guys the last 5 minutes of class on your own. I will see you guys on Tuesday for the Taylor Series test. I'm going to bring around the review. If you would like, this is a completely optional experience. The answer key is posted online. That's interesting. Cool. Thank you. And that's all I got for you today. Thank you guys for your hard work. We got 3 days of notes to go. Oh, if you want, the mock exam sign up. I think there are 7 people signed up. I would love more friends. It's gonna be fun.
Yeah, I was like, if we had 10 minutes, maybe I would. Yeah.
Oh my God, I'm so fancy. Oh yeah. And get ready for the breakfast. Oh, I'm so excited.
Yeah.
Yeah, absolutely. Just let me know if I have to bring it anywhere for you.
We'll both be at college this week for a fast.
Everyone say bye, Brendan. It was
Hi guys. Have a good weekend, y'all. Have a good weekend, Miss Stephanie.